Electron affinity is another trend. Electron affinity is the energy change when a neutral atom in the gas state gains an electron. So it's kind of like the opposite of an ionization energy. The thing about this is sometimes it's positive and sometimes it's negative. We can write an equation for it. Here's our neutral atom, and we're adding an electron. That gives us a -1 ion and an energy change. Could be positive, could be negative. It's usually negative, an exothermic process, but it may be positive. So the alkaline earth metals and the noble gases have positive electron affinities. What that means is you have to give them energy to make that electron stick. They don't want it. Why doesn't a noble gas want an extra electron? It's already good, right? It's got a full valence shell, 8 valence electrons, it's all good. It doesn't want an extra one. Alkaline earth metals, they tend to lose an electron, right? To become like a noble gas. If you give them an extra electron, they're not going to be happy about that. So those have positive electron affinities. The trends in electron affinity are less regular than the other trends. It's really almost not a trend at all. For the alkali metals, we do see that the electron affinity decreases, becomes more positive as we go down a group. Other groups don't really show a trend. We see a general increase becoming more negative as you go across a period. But again, it's not a very strong trend. Group 5 is lower than expected because that extra electron has to pair up. So we also saw a change at group 5 for ionization energy because for the 6th one, we're losing that paired electron. And we see that groups 2A and 8A have very low electron affinities because the added electron is going into a higher energy level or a higher sublevel. But for any element in a period, it's the halogen that's going to have the highest. It's going to be really happy about getting an extra electron. And it's confusing here because larger electron affinity is a more negative number, and smaller electron affinity is a more positive number. There's a table from your textbook showing different ionization energies. Electron affinities. So for the noble gases, it just says greater than 1, greater than 0. I mean. These are all positive. And so the trends they're kind of iffy in there. So let's talk about some properties of metals and nonmetals. We've mentioned some of these before. The nonmetals are sort of the not metal. They're kind of opposite in their characteristics. So metals are malleable and ductile. You hit a piece of metal with a hammer, it doesn't shatter into bits. You dent it, right? And if you keep hammering it, you can hammer it flat. That's malleability. Ductile means it can be drawn into a wire. Nonmetals are brittle. Smash those and they will break up into pieces. Metals are shiny and lustrous. They reflect light. Nonmetals don't. Metals conduct heat and electricity. That's why we use them for cookware. Nonmetals are insulators. They don't conduct those well. Most of the metal oxides are basic and they form ionic compounds. The nonmetal oxides are acidic and they're molecular compounds. Metals form cations, nonmetals form anions. Metals lose electrons, nonmetals gain electrons. So metallic character is how metal-like is this element. There are degrees of metallic character even with metals. So it's how closely does the element's properties match up with the ideal properties of a metal. And we can extend this to talking about human beings if we talk about gender stereotypes, right? So there are gender stereotypes about men and women. Not all women are wearing frilly, lacy things and like to bake and stuff, right? But some do. And others like to work out in the fields and wear jeans, and they're less classically feminine. Now, none of that is better or worse. It's just compared to those stereotypes. So here we're looking at the stereotypical behavior of a metal. So as we go across a period, as we go from left to right across a period, we see that metallic character decreases. They're still metals until you get to the very end, but they're not as classically metal. They don't fit that stereotype as well. And metallic character increases as we go down a column. I think this is actually the easiest trend to remember because you've got huge hints in the periodic table. So as we go across a period, here's sodium, magnesium, aluminum. Those are metals, right? And we get over here, is chlorine a metal? No, it's a nonmetal. So that must be less metallic than sodium, right? As we're going across, metallic character decreases. Going down, we're starting up here with nonmetal, semi-metal, semi-metal, metal. As we go down, character becomes more metallic. That makes sense? It's a more standard periodic table. Again, showing here's the semi-metals, there's the nonmetals, and here's the metals. So these are all metals, but chromium is less metallic than potassium is. So we should be able to answer questions like this. On the basis of periodic trends, which is the more metallic from each pair? Well, germanium or tin? We got to find them in the periodic table. Yeah, tin. Because as we look at those, germanium is higher on the periodic table than tin. And in fact, germanium isn't a metal, is it? It's a semi-metal. So tin is more metallic. Gallium or tin. Gallium is right over here. Can't tell. We'll go with not possible on that one. The trends oppose. So, yeah, can't really tell. Phosphorus or bismuth? So phosphorus is up here, bismuth is down here. There's some other elements in between. Bismuth is more metallic. The metals are at the bottom there. Boron or nitrogen? Boron. Boron is to the left of nitrogen. It's more on the metal side of the periodic table. It is not a metal, but it is more metal-like. Does that make sense?